Let us next differentiate the function sine. The two limits that we proved in the previous calculus video, they are going to help us in doing that. So let y be sine x, then by definition dy dx is this limit. So we are using the definition of derivative here. So the limit has the variable h and h approaches 0, and of course we have the difference quotient sine x plus h minus sine x divided by h. So obviously the next step would be to expand this sine term using the addition formula for sine. So this becomes sine x cos h plus cos x sine h, and then we have minus sine x divided by h. Since I don't have that much space here, so I have decided to write 1 over h there separately. Now you can see that h is the variable of this limit and h is approaching 0. X, although x can be any real number, x does not really change as h changes. X is constant with respect to h, and as such, these terms sin x and cos x, they do not change as h changes, and that is why they will go outside of the limiting process. Now next what we do, we collect those terms which have the variable h and put them together. Not all of them, of course, can be put together at once. It has to be done a little carefully like this. So what we do, we take sin x common out from the first and last term. So that will give us cos h minus 1, and then we also have divided by h. So we have written that h here as the denominator. And then in the middle term what we did, we kept cos x separately, and then we wrote sin h divided by h. So on this, if you apply the limit on this sum, then the limit first of all gets distributed to each term of the sum, and then from each one of them that constant thing comes out. From the first one sin x comes out, and from this term cos x comes out of the limiting process. And now you recall those two limits. The limit of cos h minus 1 divided by h as h approaches 0 is 0. And this limit, of course, is 1. So that way the final result is cos x. So regardless of what the real number x is, the derivative of sin x with respect to x is cos x. That means the function sin x is differentiable at every real number, and its derivative there is equal to cosine of that real number. Or when you think of the derivative itself as a function, then the derivative of sin x is the function cos x. Next, let us see some examples which involve this derivative of sin x. In this example, there are three parts. In part A, we are given this function y, which is x square minus sin x. So if you differentiate this with respect to x, then you would differentiate x square, that will give you 2x, minus you will differentiate sin x, which now you know is cos x. So the derivative is 2x minus cos x. So we have to use not just the derivative of sin x, but our usual rules for differentiation. For example, the difference rule, power rule, those things. In part B, the function is a little more complicated. It's no longer a difference or sum, it's the product of x square and sin x. So we have to use the product rule here. So differentiating it, first you differentiate x square keeping sin x as it is, plus you keep x square constant, you do not change it, and differentiate sin x. So this derivative is 2x, so you get 2x sin x, plus this derivative is cos x, so you get x square cos x. So that way the entire derivative becomes 2x sin x plus x square cos x. And then it's a little more complicated. In part C, it is sin x divided by x. Whenever in calculus you see a function, its domain will not be explicitly given. So if there is some problem in defining the function somewhere on the real line, you have to understand that those problematic points are not being considered. For example, here x cannot be 0, which means that it is not 0. Okay, so that assumption is there in the background. So if you differentiate this, you have to use the quotient rule. So by that rule, first what you do, you square the denominator, and then in the numerator you keep the denominator first intact, you do not change it, and you differentiate the numerator. Then minus, you keep the numerator intact and then differentiate the denominator, and of course these are products. So this one will give you cos x, so that way you get x cos x minus d dx of x is 1, so that way you get sin x divided by x square. So this is the derivative. So next we see the derivative of cos x, because already we have seen how we found the derivative of sin x, so it's familiar to us. Y is cos x, so then dy dx is this limit. The only difference now is that in place of sin we have cos. So this time we have to expand this cos term using the addition formula for cosine. So that gives us cos x cos h minus, recall that in the addition formula for cosine we have a minus in between the two terms, minus sin x sin h minus cos x. So arranging the terms is exactly similar to the case of sine. Again we take this time cos x common out from the first and last terms. So that gives us again cos h minus 1 divided by h. And the middle term is, you see, there is a high chance of making a mistake here, and especially if you write things like this, you may end up writing plus sin x sin h. It's not plus, there is a minus. So minus sin x times sin h divided by h. And then of course you know what happens after that. These terms independent of h go outside of the limiting process and we get this. So again this limit is 0 and this limit is 1. So that way we get this time minus sin x. Okay, it's no longer sin x. The derivative of sin x is cos x, but the derivative of cos x is minus sin x. We are eventually going to differentiate the other trigonometric functions also. There also you will see that all these functions which come with a cot, cotangent, in their derivatives there is a minus in the front. Let us next see some examples involving derivatives of cosine and sine also. So this next example 4 actually also has 3 parts, A, B and C, but part C is a little long, so I will do it separately. Let us see first part A. In part A we have y equal to 5x plus cos x. So differentiating 5x of course will give you 5. First by the constant multiple rule 5 will go out, and then you are differentiating x with respect to x, which gives you 1, or which is 1. So 5 times 1 is 5, and ddx of cos x is minus sin x, just now we proved it. So the entire derivative is 5 minus sin x. Then in the second one we have y equal to sin x cos x. So here you have to use the derivatives of sine as well as cos, and you have to use the product rule. So first you differentiate sin x keeping cos x intact, and then you differentiate cos x keeping sin x intact. So this derivative is cos x. So cos x times cos x plus sin x times this derivative is minus sin x. So that way you are getting cos square x minus sin square x. If you remember the trigonometric identities, you may identify this as cos 2x. There is a faster way of differentiating this by applying another such trigonometric identity in the beginning itself. If you multiply and divide this expression by 2, you get 2 sin x cos x divided by 2. 2 sin x cos x is sin 2x, and then you can differentiate sin 2x. However, at present you cannot do that because you do not know about the chain rule. that we will learn, it's coming. So that will help us immensely. Okay, but without that we have to just use the things that we know about. So this is that. Now next, let's see part C. So in part C, the function is cos x divided by 1 minus sin x. So we have to use the quotient rule, obviously. So dy dx by the quotient rule, it's a bit difficult to write it, how you normally write it. So again I have written the denominators separately. This has to be squared, of course, and that will be our denominator. In the numerator, you first keep the denominator intact and multiply that by the derivative of the numerator, which in this case is cos x. And then minus, you keep the numerator intact and multiply it with the derivative of the denominator. So d dx of 1 minus sin x. So this is outside. Then inside 1 minus sin x times d dx of cos x is minus sin x minus cos x times, if you differentiate this, differentiating 1 will give you 0 because constant rule, minus d dx of sin x. d dx of sin x is cos x. So you get minus cos x. Next. Okay, so next of course we do this multiplications, and that way we get 1 times minus sin x, which is minus sin x. Minus sin x times minus sin x is plus sin square x, and minus cos x times minus cos x is plus cos square x. So these two terms give us 1. So we have 1 minus sin x as the numerator. And this is the denominator. So after cancellation you get this. So this is your derivative. Actually, if you want, although it's not advisable, if you want you can stop here itself and say that this itself is the derivative, because you have to differentiate and you have done that. But usually it looks like a job unfinished. That is why we try to express the answer as simply as possible. But anyway, this is it. Now if you recall that when discussing trigonometric functions, we emphasized the fact that trigonometric functions are used for modeling periodic phenomena in nature. And one particular type of periodic phenomena is simple harmonic motion. Now that we know how to differentiate sine and cosine function, we are able to study that type of motion, which is what we will do in the next calculus video. We will see how these functions sine and cos naturally arise in descriptions of such motions, simple harmonic motions. So if you have such functions in, say, the displacement of something that is having simple harmonic motion, then to find the velocity and acceleration you have to differentiate, and that is why we need these derivatives. So we will see all these things in the next calculus video. And tomorrow we do not have any upload. That linear algebra, that has been shifted to some other day. You will see which day. Okay. And day after tomorrow I think we again have analysis. So see you next with that. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.